Hi guys, how's it going? My name's Akash. It's nice to meet you. I'm the fabrication specialist here at ULP. I'm a fourth year mechanical engineering major, and I come here and I fabricate and manufacture. I'm going to convince you why this job is awesome and why engineering is cool. A lot of you guys are at the stage where you want to decide what you want to do, and so hopefully this can inspire you or give you a better path on what to do. Right here, I have a file. I was just doing some typical office filing with machines. So over here, we have lots of tools. Like with different types of manufacturing, a lot of tools are necessary to get the job done. So we have like pliers, gloves, screwdrivers, wrenches to tighten things, clamps for more pressing matters.
Gosh, I just got that.
Moving on, we have a drill press. We have lots of new machines that have come to our lab. So a drill press is really great for making holes. It's good to have a sacrificial board for your parts. So this is a drill board, and you can use the whole thing. Essentially, it's always good in your designs to have creativity and toss a couple puns in. It makes everything more fun. If it's over here, we have a workbench. We have a bandsaw. It's used to make several cuts. Bandsaws are great prototyping machines because wood is really inexpensive. It's very light. It's cheap to use. And you can get you can use different tools to essentially get your prototypes. It's a good way to start. Okay, moving on.
Oh my God, we have somebody that loves puns.
Perfect. Glad to have you. I'm glad to have all of you guys, but especially you.
Now, Akash, can you really briefly, this lab looks so much different than, our wet lab side, right?
Totally.
Yeah, so can you describe some of the differences before we dive in?
Absolutely, sure. So what I love about this lab, this is the lab you want to come to really create a mess, a good mess. Like lots of debris, you can break things down, you can cut things, but you can also add things. So in the wet lab, you'll be working with more chemicals. The PPE is more involved as you'll be wearing lab coats, and it's more contained and controlled. And in the sense, we are controlled, but in a different form. This is where you really come to get your hands dirty and build. So this, and in the presentation, we'll go far more in depth, but this is where you get that idea in your head into a reality. And we're going to go through the whole procedure on that. In those labs, it's kind of like you already have your idea. Let's experiment. Let's run tests and gather data. But here it's, what do you gather data with? What are you experimenting on? This is where you create that first step, essentially. Awesome. So as technologies improved, as we started out with technology in manufacturing, a lot of the manufacturing we do is subtractive. You get a tree, you subtract it with saws, you cut it down, and you use different drills, machines, and you bring that tree down into that block of wood into a prototype. Another example is you could think of an ice sculpture. You get that big chunk of ice and you sculpt it down into the sculpture. Now we have additive manufacturing, like 3D printing. Instead of subtracting down your part, you actually create it. You add layer by layer by layer until you get your part completed. With that, we have our two Ultimaker S5 3D printers. These are the industry's top for consumer grade 3D printers at the moment. Their resolutions are really great, and this 3D printer is a staple in a prototyping lab to get your part to reality. Again, we will go into great detail on these 3D printers, but just a quick general overview of how additive manufacturing looks in a lab like this. Lastly, we have our laser cutter, which is a large-scale laser cutter. Now, laser cutters are common. This one is pretty unique in terms of the size you can cut and what you can cut. So, for example, this bed is 36 inches by 55 inches. Usually, a laser cutter would be 24 inches by 36 inches, which is about this big. It's about this big and this deep, but our laser cutter is almost double that size. And in terms of the parts, what is a laser cutter used for? Well, you can engrave special logos onto a material. This is wood. This is 1/4 inch balsa wood. And you can use a laser to essentially burn into a wood at a setting. But if you don't want to engrave, you can also cut. Something I have been working on lately. And so we have wood. You can cut foam into very particular shapes. It's a super useful machine. And this, if you could guess if it's additive or subtractive manufacturing, I'll let you think about that in about 2 minutes, I'll tell you. But what would a laser cutter be? Would it be additive? Are we adding things or are we subtracting? Okay, and then with this laser cutter, we can also create materials and such as metal. It's very unique in that it can have metal cutting capabilities. So over here, I was actually making a phone stand. We do a lot of Zoom calls and FaceTiming because of our current situation. So I was actually going to make a phone stand that could kind of float on the desk while we did those calls. So I first actually prototyped it with wood. That's what you saw on the desk earlier. And now I started with the metal to kind of compare the differences. And to answer that question, it's subtractive manufacturing because we start with a piece, we use a laser, and we burn that piece into that smaller shape that we want. So we're subtracting. Okay, that's kind of a general overview. If you guys have seen Iron Man, I love Iron Man, great movie. That's kind of what this lab is. It's like Iron Man's lab. He wants to build a suit. You need a bunch of tools, and you need that idea to help you drive that forward. And with that in mind, I want to stress that anyone can have an idea and get something built and prototype. This is the place you would do it, but anyone can think of the idea and get it started. And I want to prove that to you today. My favorite superhero of all time is Batman, and I actually drew this while I was eating my lunch the other day. It's just a sketch of Batman, his face, and just a simple dimension. I just said about 3.5 inches, 3 inches, like height, and you just need the idea out of your head. I highly recommend a piece of paper to dry idea because sometimes when you think about it, but it's not out of your head, it changes and it's kind of hard to see. Just get it out, and you can always change it and add it. Okay, so after I had my idea, I then moved on to Solidworks, which is a 3D engineering CAD modeling. CAD stands for Computer Assisted Design. And it's essentially a program where you can add and draw sketches and turn a 2D model or a 2D drawing into a 3D model. Doing that unlocks probably the biggest door in manufacturing. Now my idea is not only out of my head, on a piece of paper, and now it's in a computer. And with this program, there's several things I can do. I can put it into the laser cutter. I can put it into the 3D printer. It goes on. That's a little foreshadowing because yes, we are going to put it into the 3D printer. After I get my SolidWorks model, I would put it into a 3D printing software. Now, it reads .stl files. So I just saved my model as a .stl file. And as we can see right here, I'll actually scale this up for you, make it 100%. This is the Batman that was generated from my 3D SolidWorks model. I then went into the settings of this 3D print over here. And again, we're going to go into more detail on that. But I loaded my settings onto that 3D print, and then I put it inside the 3D printer via USB. We can also do it via Wi-Fi. The technology keeps growing. And we have our part. And so the finished product of that example is this Batman right here. So this is a very brief overview of how parts can be created from your head to a reality. Now, the possibilities are endless. And if you run into errors, which you most definitely will, it's all part of the engineering process, it's okay. You learn from your mistakes, and those errors will save you in the long run. So what I want to emphasize again is get those ideas out of your head. So just a comparison, here's the drawing, and here's the 3D model. So take a look, see if you can spot any changes or differences.
Now, Akash, what kind of training do you need to take that sketch into SolidWorks? Like, do you have to take some courses or?
Totally, that's a great question. So the official training is you go to a college, you take an engineering class on 3D SolidWorks design, and you essentially learn from that class. Now, I didn't do that, and you guys definitely don't need to do that. I actually learned SolidWorks on YouTube, and it was an Iron Man mask, ironically. I learned through YouTube tutorials, and SolidWorks you do have to pay for it. It's not free, but it's not the only CAD modeling software out there. There's millions of free CAD software. There's some really good ones too. It's just the concept. So I actually learned SolidWorks on YouTube, and I was a junior in high school actually. And I really love to draw, and the 3D world just really seemed like a cool option. I will say that I did also take that SolidWorks class in college again, and it wasn't what I expected. I still had to teach myself most of the work. The professor would lecture mainly about the history of SolidWorks, and it was up to me to learn how to model it. So I'm trying to save you guys that step and say that you can learn it on your own, and you can start right after the Zoom call if you wanted to. So with that in mind, I think it'd be a great time to make a Batman from scratch, just to show you guys what the process would look like. A common question I get is, okay, well, these Ultimakers seem really nice. Can I get one? Yes, you can. They are $6,000. So is that very practical? Maybe not. But these aren't the only 3D printers out there. In fact, there's several 3D printers you can get for $100 or above. Like from the price range of less than $500 to about $100, you can get a great 3D printer. In fact, after learning these settings that I'll actually teach you guys today, I was able to buy a 3D printer for about $300 and get like good quality parts that could compare to these machines with a couple settings that you tweak. So this world is very user friendly, and I encourage everyone to give it a try if it's something you want to go down. Okay, so with that in mind, just to reiterate, started with the sketch, and from the SolidWorks model, we put it into Cura. Oddly enough, the printers are $6,000, but Cura is completely free. And it's completely free to download, and it works with all kinds of 3D printers. So I actually use Cura with my 3D printer at home. And so what we're going to do is we're going to print this part onto the machine. So the first thing I'm going to do is using the file open command. My Batman part is right there. I open it into this machine, and it's right there. In fact, I'm going to just delete him and just show you from scratch. So I just go to Files, my Batman bus from the SolidWorks file. There he is. He's plopped into there. We're going to cover a couple concepts that a 3D printer uses, such as infill density and generating supports. And we'll just go through that step by step. So the first thing I'm going to do is rotate the part so it is in the center of the 3D printer. It's always good to do this because the center is where the most heat lies in a 3D printer. And as we get this part set up, actually, before we get this part completely set up, let's take yours over to the printer and let me explain a little bit of how it works. So this is what we call an FDM 3D printer. Has a fancy long name, but essentially FDM means you get a roll of filament or plastic right here, and you feed it. Oh, let me grab a smaller one to give you an idea. So you get a roll of plastic, and this is known as filament. The plastic we're using today is PLA. It's the most common filament in a 3D printer, and it stands for polylactic acid. It's a great plastic because it heats up really well and it cools down really fast. So essentially what we do with this roll is we feed it into the back of the machine. It goes through a tube right here. It's called the Bowden tube. And it gets fed into an extruder. Now this extruder gets very, very, very hot, and it extrudes the hot molten plastic onto the printer. And this is called the build plate. And layer by layer, the part builds up. And so this plate needs to be warm so that the plastic part gets held. And that's why in this software, if you look, it actually says Ultimaker on it, because I set our printer as an Ultimaker. And this is actually that glass build plate that you see right here. Just to give you that, what we're looking at in the software is this in real life. So with that in mind, I'm gonna center the part so we get the best temperature for this piece. I'm gonna scale it down. Right now it's at 100%, but I want this part to be done during this class. So I'm gonna actually scale it down to about 25%. We're gonna have a mini Batman. The next thing I'm gonna do is I'm gonna set the profile of the printer. It can seem confusing at first, but it's just the resolution of the printer. My favorite example is a YouTube video. If you watch it at 1080p, your video is going to be extremely awesome quality, but it's going to take a really long time to load. If you want a quick video, you'd probably watch it at 360p. You'd still get to watch your video. It might not be the best resolution, but it's quicker. In the same sense, with the 3D printing profile, extra fine is that 1080p video. It's like extremely accurate and detailed. Fine is still really, really good. And normal is like, normal in an Ultimaker is also amazing, but it's not the best. But in the end, we still get our part. For today, I'll do fine. We'll go right in that middle ground. Okay, moving down, I will be setting the infill speed, the print speed, the infill density, and we'll go over that. We'll go over that in way more detail. I just want to get this part fired up, and while it's running, we can discuss these concepts. So coming right here, I'm going to set the print speed to 80. I'm going to set no supports, no build plate adhesion, and one more is the infill density, which is right here. And we're going to actually set this to a zigzag pattern. And just keep these words on the back of your mind, because I am not expecting you to understand this until I explain it. So just to remember though, let's see if people can memorize this. I have an 18% infill density and a zigzag infill pattern. Okay, and I'm going to go down and I'm going to slice this print. And it says 18 minutes. So in 18 minutes, do we have 18 minutes? Yeah, perfect. We have 18 minutes. So I'm gonna get this USB drive from the computer, from the printer. I'm gonna plug it into the computer. And also, something like timing is always an important part in rapid prototyping. So just to prove that, I'm gonna actually try to speed this up a little more and say, I'm gonna change this to normal. I'm gonna keep the settings. The infill density is still 18%. And I'm actually gonna change that print speed. So instead of 80, I'll make it 85. And yeah, and then I'll slice that up again. And now it's gonna be done in 12 minutes. So we saved 6 minutes of more concepts to go over. Save to the drive. And I'm gonna eject it. I'm gonna plug it into the printer and let it do its thing. So you just plug it into the printer. I'm gonna select my part. You see Batman right there. And right there it says 12 minutes and 18 seconds. I'm gonna start that print and let this thing go on its merry way. Now, I know just now we went over lots and lots of information. So let's now break that down and really understand what's going on. So a couple things to think about. When you rapid prototype something, you always have to think about how much material are you using? What is your part? Are you orienting the part correctly? And how long is it going to take? What are you losing? Like, are you willing to spend a longer time doing something and making it look really crisp and clean? Or do you just need something that you can saw up or drill a hole in quick? Okay, so concepts like that include that. The first one is profile. Do I want the best print quality possible? I put it at fine, but to speed things up, I said we'll put it at normal. We'll test it out. So, okay, infill density. This is probably the most important concept to think about in a 3D printer. So I have prepared a piece of paper right here. And just, I want to make this as simple and basic to understand. So I'm just going to draw it from scratch in a Sharpie. Let's say I look at this Batman. How much plastic is actually filling this Batman up? Well, that's the infill density. How dense of material is getting printed inside of this Batman? So let's just say I'm looking at Batman from the top and I slice a little cross section from this Batman. Hope everyone can visualize that. Like, let's say I slice a cross section of this Batman and we're viewing that from the top. So we're looking at this. And just to really show, this is Batman. All right, give him a smiley face. And we're looking at him from the top. And that's our eye. Looking at him from the top, and it's a cross section. Okay, so infill density is how much plastic is actually getting put in it. And if you guys remembered that term, I said 18% with a zigzag. So 18% with a zigzag pattern looks like this. So it's zigzagging like so. And it's crossing like that. So this number is telling my part that the amount of lines you're seeing, these black lines are the plastic getting made. 18% is saying these are how many lines you're seeing. So if I do the exact same cross section of this Batman with now 100% zigzag, it's gonna look like this. Like it will be, I should have drawn this much smaller, a lot of shading. It will be that dense with plastic. Does that make sense? So the infill density is how much plastic are you filling inside of this? So when you actually pick this up, if I'd made this at 100% infill density, this thing would have been like boom, like very, very dense and packed and heavy. There's much more material. Now, with that in mind, things to consider is with a higher infill density, your part will be much stronger, right? Because there's so much plastic in it, it's going to be a much more dense part. That will take, it has limitations as it will take much more time to print and lots more material. So 18%, you kind of have to work with what do I need? What is this application? Is this Batman going to withstand a lot of force? Probably not. Probably use him to hold some papers down in the wind. 18 was fine. 18 was quick, and it's light, and it saved a lot of material. So another important concept, and so one last thing I'd like to emphasize with that is zigzag there's several other patterns that can be made. Zigzag's one of them, but let's say I was printing a tube or like a rod, plastic rod with material. I maybe would want to do a concentric, which just means circles, infill. So instead, maybe I'd want it to, and let's say I said 20%. I'd fill up that plastic. Does that make sense? That would be the rod right here. It'd be the cross section of this rod. Okay. The other thing to think about, again, your ideas should be infinite. Like, do not be limited by the machine's limitations, because one day there will be a technology where you can make those happen. So you should always think outside of the box and see how you could get your part to work. That's all engineering is. You have a problem, you want to solve that problem. A big problem that's constrained with these machines is the concept of supports or overhanging parts. So a 3D printer, if we're looking back here, is going to shoot out this plastic through the top, and it's going to build a part layer by layer by layer until it's done, right? How do you build something? And like, we're looking at this from the side. This is a side view. How would you build a part that looks like this from the side or with a 3D printer? Same concept. We have the plastic coming in from here. How does this get created? If you're building this up layer by layer, what happens here? This is technically floating in air. Wouldn't your part kind of fall over? How does that work? Well, a 3D printer, what people have thought of, one is, how do you orient your part to make sure it can work? I'm kind of lazy, or I don't like to use the word lazy. I like to say I'm efficient. I would rotate this part like that. That's an arrow. So that it looks like this instead. So now the printer could print it layer by layer and nothing's floating. But let's say you can't and it has to be floating. There's no other possible, this won't work. You could generate little plastic supports instead that also print with the part. And then they actually hold this up so that it's able to print. And that is one way to solve these problems. And the reason I want to bring that up is right now, with this technology that we have, it's an issue. So maybe after this talk, you think about it, come up with an idea where we don't need support. How could we build a machine that could actually improve this technology? With that in mind, this Ultimaker is special because it has 2 extruders. So we call it a dual extrusion 3D printer. What that means, another popular question I get is, okay, well, so instead of plastic coming out of 1 nozzle, you can actually have plastic coming out of 2 nozzles. This opens a huge world. The first question I get is, okay, yeah, you can 3D print different colors, right? Yeah, you can. So you can print a multicolored print and you can switch out the colored filament. So you could get like a rainbow print, essentially. The biggest use of a dual extrusion 3D printer is water soluble supports. It's called PVA. It's polyvinyl alcohol, but it's essentially Elmer's glue. And what it does is now that we've learned about dual extrusion, we have the second 3D printer nozzle here. So this is number 1, and this is number 2. In this one, we can actually make a PVA water soluble material where when you put it in water, it dissolves and it goes away. It takes about an hour or 2 for the plastic to kind of melt down and dissolve, but you have a clean part. So that's one way of unlocking that geometry. Now that you kind of got the brief overview of printers, let's check out our Ultimaker and see how this part is looking. If you look closely, you can actually see the 2 nozzles, and they're building up Batman from scratch, layer by layer. Essentially, you see this glass plate is just, it's gonna go down. It's slowly moving down as the part is growing, right? Because it has to start up from the top, and then as the layers increase and increase and increase, the plate will go down. So you could actually print a Batman head that was probably that big. Just take a lot of time and a lot of material. Another common question I get is, okay, so how big can a part be to 3D print? It must be the size of this machine, right? It must be this build volume. Well, actually, no. Yeah, that's our current limitation right now, is that's how big one part at a time can be printed. But engineers have figured out that you can create the same product by drilling holes and mounting and connecting them together. So you can infinitely expand this part. Sure, it'll take some time and more design effort as to connecting those parts, but it's not impossible. So you could technically grow a part. We actually had a lab user in this facility build their own custom biomedical device. And surely, like a box, they built wall by wall by wall and made a big part connected. And that's why a lab like this is so great, because you should never limit yourself to one technology. You should figure out how to combine each technology you have to make that impossible idea come true. So you get a couple bolts, nuts, and screws. We could go to the drill press, drill a hole into your part, use socket wrenches, and tighten that part together and build what needs to be built. Going back to our part, I want to also bring up that we get a time estimate on the part. Now, I used the word earlier, slice. And essentially, what it's done, when I click that, now it says save to file, but earlier there was a big blue button that said slice, and I'll get it there in a second. And just for this demonstration, I'm going to make Batman now. Let's make him 400%. Okay, that's maybe a little too big. Let's go 200%. Okay, now everyone can see his face a little better. I'm going to slice this part. And again, we're going to go back. And now I think this will be really cool to show you. Now that we've got a brief overview. Over here is our infill density. I'm going to go ahead and change that shape to triangles. Okay. And I'm going to now click this button where it says slice. And it's going to generate a time. And what it does is it takes apart that STL file and it will go layer by layer and tell me a time estimate. So this Batman right here, if you go down right here and you see, is now 13 hours and 35 minutes. But because I sliced it, we can now do a couple cool things. So we can come here and if I click preview, it's going to process every layer. We can actually watch this Batman get built layer by layer by layer. And that's exactly what the 3D printer is doing. Now, something I want to show you guys and emphasize is, do you see these triangles right here? Here's a question that you should think about. I'll explain it in just a second. Right now, we made this infill density 18%. And does everyone see the triangles and see how far apart the triangles are? I am going to now change the infill density to 100%. Actually, no, I'm going to change it to 85%. So instead of 18%, I'm going to now make it 85%. Are these triangles going to expand, get bigger, or are they going to actually reduce and shrink in size? Just keep that in the back of your mind. Let's go through and see. I'm going to come back here and change that infill density to 85%. I'm going to slice it again. The computer is going to generate. Okay, now that the part's so dense, it's now going to take 1 day, 6 hours, and 1 minute to work. And another quick question I get is, how much material does this take? Well, it says right here, this large Batman, it's probably like about this big in real life, according to the model, would take 545 grams of filament. You see that right here? Each roll that I showed you has 1,000 grams of filament. So this is half of one roll. So now, going back to that triangle question, we're going to go back to that preview. It's going to process the layers. And for those of you who said the triangles would reduce in distance, you're right. Because in theory, if it was 100%, this would become one solid block. And that's the exact same concept that we showed on that paper earlier. So 18% infill density, these are those zigzags. They're really, really, really far apart. And now at 100%, in theory, you should see no white lines. It should be one solid chunk. And with that in mind, there's so many patterns. You have triangles, lines, grids, concentric, zigzag. If I'm being 100% honest, how did I discover these shapes and how did I discover different parts? I messed around. One day I clicked on that and I said, what's it gonna do? You gotta be curious in engineering. As long as you're not hurting anyone and you're being safe and you're prototyping, prototyping is all about trying new things and seeing what works best. You're gonna learn either way. With that in mind, coming back, we have 10 seconds left on this Batman and we're now about to see his ears getting printed. You can watch the printer jump back and forth. And it is now finished. And now we're gonna watch the printer cool down because again, we were melting plastic at a super, super high temperature. And now we gotta let it cool down and come back to that room temp level. We want it to be a nice solid chunk of plastic again. And while this Batman's cooling, I'll take it out and we can watch the printer now telling us, okay, he's done. We're gonna I'll open it. See, it says finish print. and now confirm removal. A 3D printer extruder gets to about 220 degrees Celsius, and that's when it melts the plastic. Right now, this bed is about 80 degrees Celsius, and we're just gonna let it cool down. So I opened these doors, and I just want some airflow to go to the Batman. In about 2 minutes, 3 minutes, we can take him out and observe the part. But I would love to answer any questions, because hopefully there's a lot. If I had watched this, I would have had a lot of questions. So please shoot away.
Thank you for sharing, Akash.
Definitely.
I know nothing about 3D printing or engineering at all.
Totally.
I teach biotechnology. Are the skills that you used in the program today, are they applicable to other programs? Or will you have to totally learn a new system?
Okay, totally. So by other programs, do you mean other 3D printing programs? Just to get your question. Yeah, absolutely. Every term I used is in all 3D printing programs. I've used 5 3D printing programs. There's another, the competitor. So we like to, in the 3D printing world, we joke, Ultimakers are kind of like the Mac, the Apples of the 3D printer. They even kind of look like Apple products. If you didn't see it, it's an Ultimaker. There's another brand called MakerBot, kind of more on the PC side. They have their own free software too. And I think it's MakerBot. I think the printer is called a Replicator. Infill, patterns, speed, it's all the same. So you can think of it as cars. One's this brand name car, one's the other brand name car. But what I taught you guys is what a steering wheel is and what the 4 wheels are to move the car. So absolutely.
I have a question, Akash.
Yep.
Now, our students here today are in, some of them are developing medical device prototypes, right?
Right.
Can you think of some applications that maybe you worked on, like I know you're going to school for mechanical engineering.
Right.
What other different pathways in engineering, if you really wanted to have a, let's say a biomedical or healthcare focus?
Right.
Can you
Absolutely.
share some of that?
Absolutely. Yeah, that ranges, that's an incredible range. I have lots of friends who are biomedical engineers. The nice thing about a mechanical engineer is they're needed kind of everywhere, which is cool because I've got to witness how it can be applied. I had friends and I've seen companies work on prosthetic limbs. They've prototyped plastic joints for, like, let's say a knee, and it can go back and forth, down to a way small, because a lot of bio-oriented projects are now very small. They're microscopic. We have another set of 3D printers right there, if you can see that. Actually, we can walk over. These are called the Form 3D printers, and they print on the micron level, and it is applied in dental products. So any devices with dental, you can actually get a bio-friendly resin that can make dental products on that micron level. So you can go anywhere from prosthetic limbs to, let's walk back to the 3D print. So we can do anywhere from prosthetic limbs to dental products. To simple things like, hey, we have a medical machine, but we're having trouble mounting. So even in the other labs, in the wet labs, let's say you have an issue where you're holding pipettes or something, I don't know, you need something mounted. Instead of buying something or having a kind of unsafe setup, you could use a 3D printer with the software to say, hey, wouldn't it be cool if we had something that mounted to the table and grabbed our device? And then once you get that idea, draw it on a piece of paper and you could actually make that. So the range is universal. Think of this as like a empty canvas.
Now, what kind of skills or, what kind of characteristics for an engineer, right? In this kind of space, what type of qualities do you think, a student, or, have a particular interest, like, what are your recommendations in regard? What type of student do you really see entering into this field of, mechanical engineering, biomedical engineering?
Absolutely. That's a great question. Honestly, there's one skill, maybe two, that are just crucial. One, do not give up on yourself. In engineering, you're going to see, like, for example, this whole time, I didn't want to tell anyone, I was actually crossing my fingers. I really wanted this part to work, but there have been so many times just the printer gets clogged. I messed up on a dimension or a geometry, or maybe I typed a setting in wrong. You will run into infinite, countless amounts of errors, and the last thing you want to do is get disheartened. So be persistent and determined. That's the best skill, I think, to really keep moving your products forward, because the second you give up, you could have realized that you were so close. Like, you could have realized there's just one small mistake you made, and if you had changed that, your part would have worked beautifully. That's one skill. And the other one is it's just be creative and just think outside of the box. But even the simplest ideas make the biggest difference. So don't think that you have to make something complex to make an engineering product. Sometimes the simplest idea is what helps the most. So just keep being creative and persistent.
Great. And it also sounds like you need to be like an innate tinkerer. You just like to tinker with things and
Yeah,
touch things, right?
definitely. So it's actually really funny. I've always, like, when I've had like a toy growing up as a kid or something, if it broke, I'd love to fix it. That's me. Personally, I have lots of engineer friends who've never done that before. They're really good at memorizing data or reading books, really good at absorbing information. That's totally fine. Engineering is such a broad field that really, like, any personality could fit in it, as long as you're willing to accept that your part won't work at first. It goes back down to that, because we always need someone like me, for example. I love to tinker, I love to make projects and fix things, but sometimes the theory gets a little muddy for some concepts. I have friends who are sharp as an arrow and say, hey, your part's not working because you didn't analyze this aspect, or you didn't check this dimension. So that's totally fine too. It's all about what interests you. You got to do what interests you, basically.
Now, I know you're going to be a senior this fall at UCI.
Yep.
Can you tell us a little bit about how you found, well, number one, how did you end up here? Like, you're a student, you're not from here in California.
Yeah.
So can you share a little bit about your journey and how you ended up at being our fabrication specialist at ULP?
Totally, yeah. So in high school, I'm born and raised in Los Alamos, New Mexico. No, it's not Mexico. It's next to Colorado. It's in the U.S. A lot of people always ask me, they're like, oh, we've never been out of the country. And I'm like, okay, but I'm next to Colorado. I was born in a very small town up in the mountains. That the town actually built the atomic bomb for World War II. It's now a scientific laboratory. And I was 17 years old, and I said, man, I need to get out of this town. And California just seemed like the fun place to be. So if you guys, like, when you're in high school, take your academics seriously, and your tests, go do your community service, because it'll pay off. Get to that school or somewhere you want to be. So I came here to Irvine, started taking classes, and I actually started working at the 24-hour fitness gym. And I said, man, I need to get out of this place. And so I started applying for jobs, and I found another company that did 3D printing. And the skills I learned for that company was actually through UCI. I was bored one day, and I said, hey, that shop has 3D printers. I wonder if I could go in and get my hands dirty. Like I would go into school and see my hands were too clean, and I wanted to build something again. And they trained me on how to use the printers. It was an open facility for engineering students, and I used those skills to get into the other 3D printing company. And then I heard about ULP from working at that company, and I was lucky to come here.
Now, once you finish school next year, I mean, where do you see yourself? What's your career trajectory? Like, where are you going to go? What are some of the occupations as a mechanical engineer that you're going to do? Are you going to go straight to work, or do you think you're going to spend a few more years in school for graduate school? What are your plans, and what is your thought process where you're going to this next level?
Definitely. Just being in this lab alone, another, I guess, backstory is like I love working in my garage or in my backyard, just doing something. I realized that this field of rapid prototyping engineering is the field that I've always dreamed of doing. This is the one field where I can come in, get my hands dirty, and build constantly. So something I want to do is eventually start my own company, my own idea, and build that from the ground. Now, whether it's me working from my garage at first or gaining industry experience, these next couple of years, I would like to learn. I just want to learn more about how the industry in engineering works. And my dream goal is to then start my own product or company, trying to use the same techniques I've learned here, essentially.
Fantastic. Now, you work with a lot of our startups here. And can you tell us a little bit about, how you help them? What is your role? Like some of the problems you've encountered?
Definitely, sure. So actually a lot of the 3D printers, 3D printing or design geometries, everyone has issues, and sometimes it's like you just need a fresh set of eyes. So something for me is I will suggest, hey, maybe the exact, what you saw here. A lot of times companies will come in and they have a beautiful product that looks like this. And they say, hey, it keeps failing on the printer, what's going on? And so my role is, hey, I've broken a lot of things. I realized when I rotate it, it works better in this orientation. So a lot of the things we go here is I tinker with these machines. I learn how to fix them. So when companies have that idea and they want to get it onto the tracks as fast as possible, I could try to give them insights on what might fail and what might work. And maybe in their part, in their 3D part, I say, hey, can you reduce this size or increase this so that the printer can work? And that comes from breaking or fixing and failing a lot on these machines.
Now, can you tell us a little bit? You also worked in the academic lab, right, at UCI,
Yes.
the fabrication lab. Can you tell us some of the differences between working in an academic setting versus working in a more of an industry setting? Like, what do you see are the key differences? May it be the pace, may it be, can you do a comparison, what you liked about each? And
yeah, absolutely. Well, for one, in any academic setting, be ready to take quizzes and tests and documents and lots of training. Because in academics, they need everything. They need to make sure you have learned and mastered the material. This being said, sometimes the funding in academics, the tools might not be as nice, or the machines might not be as nice. And it might be a more laid back setting because, again, we're working off of academic funding under a professor, maybe under a TA, just another student. In an industry, the first thing is you look in the lab, it's much more clean and sleek. You can't leave, like if you look in this area, even like we have a tenant right now, a resident working, everything's together. It's clean and intact. You can't leave a mess. You won't see a spill on the floor. And it is much more accelerated and driven. It's not laid back, but you shouldn't fear that. It's actually very rewarding because the work, it'll always keep you on your toes thinking, and it's a fun challenge. Sometimes in the academic labs, it could get laid back where it's kind of quiet some days, and it's not as driven as an industry that has deadlines and demands.
Great. Which one do you like better?
I love the industry. This is awesome in like a lab like this, because also as a college student who likes to do projects on my own. Actually, I bought a saw the other day. I always have to go find that good sale, or maybe like a broken machine that I fix. I always have to look more on the discount because I have that college budget. In an industry lab like this, where we have the funding and grants to achieve big goals with very nice machines, it's just really cool to see how useful a good tool is and how good a nice price machine is.
Great. Now, as our students are, Rachel, I don't know if you have any thing to add, but our students here are prototyping and drawing, and really literally drawing up those sketches, right? And going to be pitching to our industry folks on Thursday. What kind of last minute advice do you have for those that are creating that prototype, or to address that unmet pediatric clinical need?
Absolutely. Well, my first main emphasis is keep on drawing. Keep on drawing. Because I saw this and I said, hey, his nose kind of looks kind of lame. Let me go edit that. Keep getting those ideas out of your head. It will help you in the long run. And the other one is, when you present your product, especially if it's a prototype, be ready to get critiqued. And when I first started, no one likes to get critiqued on something you worked really, really hard on. There's lots of hours, like blood, sweat, and tears that go into this. But remember that a critique is probably the best thing to happen to your product, because they will expose potential failures or fixes that you can do to make that crisp product. And 5 months down that line, that critique could have helped you and saved your product. So when you give a speech, someone says, and you present your product, if someone says something about it, don't be disheartened. Take that critique with pride and understand it's coming from a good place.
I like that. Rachel, anything to add before? What are you printing over there in the other Ultimaker?
This one, it's a resident that's using it. I can kind of look. One thing is, this is a special print because it's ABS. It's not PLA. So yeah, the 3D printer itself is actually just this chunk right here. This big, gigantic cover is actually a fan filter unit. Now, ABS, when you melt it, releases fumes that aren't good to breathe. They're not the best to breathe. So this is actually a filtration unit that came with the Ultimaker, and it's filtering out the fumes, so it's safe for us to be here. And so ABS is a great material because it's much more durable, and that's why it's a plastic. It's a common plastic that most people have heard of. Like, oh yeah, that's ABS plastic. And so yeah, they're probably building it for some kind of mounting bracket I see by those holes and squares.
Awesome.
And lastly, sorry, our Batman has completed. We now have a miniaturized Batman. And we can put him right here. So
Thank you so much, Akash.
Absolutely.
I learned a lot. I knew nothing about 3D printing before this.
Absolutely. And so I honestly, it's a great hobby. They make some really user-friendly printers. I honestly, 5-10 years down the line, I think most people will start having 3D printers in their house. I think it's going to grow into something much bigger.